Well, good morning. First, I'd like to thank Lucas, Mauro, and all the organizing committee and the people he's working. Very well done job. Congratulations. As Professor Loret said yesterday, it's very important to continue to develop the theory in South America. So thanks for that, to continue to work on this. Well, for me, this workshop is very special because, you know, there is some mini course here, linear control systems only groups, something we start to develop 20 years ago, a little bit more. So thanks, Alexandria, João, for this, this effort. Today, I do not intend to be technical. Actually, I am not a researcher in Lie theory, but just I use a couple of things of this very nice theory to apply for some special classes of control system we call linear control systems on Lie groups. So let me start with a very famous and very simple example coming from this very nice book from Pontryagin, 1962, which is this one. The problem is to stop a train at the station at minimum time. So you have, here you have the railway, here you have the station, and let's see, so x of t will be the distance between the train and the station at the time t. You see, of course, x dot is the velocity. So I have here the distance. Here I have y, which is the velocity.
Is that small?
Yes, the driver is very smoker. 20 years ago, this guy died. So you see, so the geometric meaning here is to translate, because here is the train and this is positive velocities coming to the station, to translate this initial condition to the zero, to stop the train. But it's not any curve. It's a special curve which is an integral curve of the systems. If you look here, x dot equal y, y dot equal acceleration, u, this expression is, you can write this way in matrix way. About the control, it just are some admissible class of function that allows to compute the solution. For example, a locally integrable function. So you see you have some u up to the time, sometime, depending on the control. And in that case, we consider this guy, because 1 represents the maximum acceleration and minus 1 the maximum brake. So you can imagine a lot of possibility here. So the answer is very natural, but at the beginning, how to select a special control to do the target. Okay.
You want to minimize TU.
You need, no, this is time, you mean the time. So you need to find some control such that the time you reach.
But it's not TU. TU is just a parameter.
It's a parameter. It's, you don't, because it's arbitrary, depends on the control. It's just the extremity of the definition of the control, right? Okay. Well, this is, you see the expression here, it was x, y, dot, a matrix, the element in the space state, plus u1, u. So, of course, here is R2. The question is, first, how to translate this problem to general Rn. It's very easy because you change just any matrix, and here you can have more than one control. So you will have something like a n by m, with n is the number of the controls. And then, from the Euclidean space, to go to Lie groups. So, what kind of problem we would like to address today? Controllability means that if you have, let's say in general, a control system is a family of vector fields. Any control here gives you a differential equation. So you can think about geometrically, you have a manifold, a family of vector fields. Then you pick 2 points, and you want to find a special integral curve of some vector field to transport this point in positive time to this one, and also from this one to this one. This is the controllability, but controllability is very rare. You see, it's put some money in as investment in the bank. You want to have double tomorrow is not possible, right? Okay, what is control set? Control set is more real because there are a special region of the manifold that you have controllability inside, in the interior. Okay, this is more real. I will say something about the Pontryagin Maximum Principle from the Euclidean space very geometrically. If I have time, I will give you the expression for the generalization of the linear control systems on Lie groups. And I don't know if I have time to say something about almost Riemannian structure, which is very related with this kind of controls. So here you have, you see, the matrix we defined before. And here is the expression of the solution. This morning, Joao was computing in a very nice way. Something that I want to remark, you have two possibilities for this omega. When omega is all the Rm, which is like a mathematical issue, because you see it's not possible to apply in real life. And this is, we call unrestricted case, and when sigma is normally a compact convex subset, this is more real, this is a restricted case. But in this case, Rm, when you start from 0, this set here is all the state you can reach from the 0 by using all the possible control. You see, this is a machinery of differential equations. You start from 0, you choose u, you put in this machine, you have a solution, and you go up to the same time. See, this is very easy to show that when you start from 0 here, you can add u1 plus u2, for example, two different points. And again, since omega is Rm, u1 plus u2 is inside. So it has a structure of a subspace, right? Okay. Normally, the algebraic point of view help people saying, in this case, you don't need to compute all the solution to know if your system is controllable or not. Just compute this matrix. You see, B, AB, A square B, A n minus 1B, and the Kalman rank condition of the Kalman condition say that if this matrix is the rank coincide with the dimension of the space, so you have controllability, which means any 2 points you can connect. which is equivalent to have controllability from the 0 position. In our case, the chain, do you remember? This is A, and this is B. If you compute B and B, this is dimension 2, so you have controllability. See, almost free, you know this problem, you have controllability. Now, since any point, from any initial condition, I can translate this point to the origin, now I can ask what is the minimum. Because you need to be sure that there exists at least one. So in this sense, it's very nice, this approach. But what happens when you are in the restricted case? In the restricted case, we have this theorem. When the system satisfies the Lahr condition or the Kalman condition, B and so on, generate all the space. In that case, it's a necessary condition. You have that there exists only one control set, which is given by the closure of the positive orbit with the intersection of the negative orbit. Negative orbit means all the element that you can transport to the origin with the system, right? In a special case, you have a controllability result, global. You see, this is for restricted case. You need something more. You need to the hypothesis of the diapone of a spectrum, your matrix A, is 0, which is the case here. You see? So for the chain example, the Kalman condition will not give you, except because this is okay here. So now we know there's you can connect any 2 points in the plane. All right. Let me try to explain what is the meaning of control set by this nice example from the book of Colonius and Kleeman. In general, a control set means some region that if you take a point in this control set, you need to find a control that the positive orbit should be inside for every t. Second one, if you take a point and take the positive orbit of this point, then the closure of this set should contain the control set. And the control set is maximal with respect to these two conditions. So here, this is the system. This is the system. And you have, when you choose -1 and 1, you have two saddle points. And the control set here is given by this region here. Take any point here, for example here, you can construct a loop inside, right? So you have a control which is remain inside. Look at the positive orbit of this point. The positive orbit that you see, you can reach all this stuff and also there. So you have all this region. This is the positive orbit. And then you take the closure. The same is here. You see, you take any point here, you go there, and you enter here. The same is true here. This is a place you enter. So you have the intersection of this open set. You take you take the closure. You intersect with this set, and you obtain this control set. Okay? Right. Let me give you a geometric meaning of the maximum principle. You probably know this theorem get the Lenin Prize in Russia. It was the era of Cold War, see, and they had this prize. So this is very important in application. In nowadays, in all this stuff about sub-Riemannian structures, again, it's very important, this principle. But this is just from geometric meaning for optimal problem. So, look, then you have x, right, x, And you can reach some special point here at minimum time. So according to that, Pontryagin proved that the accessibility set from x up to the time t satisfies all these properties. Compact, convex, it deforms continuously with the Hauser metrics, and another things that I explained few minutes. So, okay, this is, assume this is AT. Assume this is the optimum time. So, what are the possibilities for your y? Of course, y cannot be outside of the free. But also, he cannot be inside. Why? Because you deform continuously. So it is an open set. So the only possibility for this guy is to belong to the boundary. Right? But this set is compact. Compact you need to apply the Hauser metric. But it's convex. So you have the Hahn-Banach theorem, and you know you have all this hyperplane in the same size. So you have this vector let's call lambda t bar, all lambda y, this point is y, lambda y, which is interesting that any point here, remember all these elements are points you reach from x at the time t. If you translate everything to this frame, what happened that the inner product between these two are negative. See here. And the optimum you reach exactly when you have 0, which is exactly this point. So this is the geometric idea of when Pontryagin proved this theorem. This is just a corollary. The first proof was more than 100 pages, right? Really. And he realized that Bellman published, this is the principle of Bellman, which is very easy to understand. He said that if you have an optimal curve connecting 2 points, if you choose any point in the middle, so this is optimal and this is optimal. So it's not just one vector here. You have, because you repeat the same situation, do you understand? So you have a one parameter group of a vector of if these elementals are in the orthogonal, the cotangent bundle, right? Because of that, this set you need to put in the cotangent bundle of the manifold. If I have time at the end, I will explain how to solve this problem of a motivational problem. Okay? Right. Let us go to the Lie group. So what is the correct generalization from Rn, or from Euclidean spaces, to a Lie group? First, take a look here, the drift. The drift means the vector field that you are going to control. This is linear. And here, we will see in a moment that the column vectors of B are constant vectors on Rn, which means they are invariant vector fields. So, specifically, the dynamic of Rn, the drift is linear. The control vectors define any m invariant vector fields. And at the first glance, when I was trying to understand this, I imagined immediately that, of course, e to the power ta is a one parameter group of automorphisms of Rn. So if you want to generalize, you can ask for the flow of x to do the same. Means the flow of x, your candidate for linear system on the group, should be a one-parameter group of automorphism of the group. But Professor Tirado asked me, it was in ICTP, asked me, you don't have any more algebraic condition? I say no, but after one day, we came with this, finally we understand what the meaning of Kalman condition. Do you remember you have B, AB, A squared B, and the Lie bracket between AX, the matrix, the linear differential equation determined by A, and any vector field invariant, give you another invariant vector field, which means this matrix is leaving invariant the Lie algebra, right? So, of course, the first thing was consider the same for the Lie algebra G. So you have a group, you have a system, and you have the Lie algebra. Consider all the infinity vector fields such that normalize the Lie algebra G. And we were able to prove that in the simple connected case, this set is a semi-direct product between the Lie algebra and the derivation of the Lie algebra. Of course, the Lie algebra should be here because it's the definition of Lie algebra, but the derivation also. And in the connected case, this set is the Lie algebra of the Lie group of automorphisms, which is also contained in the derivation. But you could have element here, when you are in the connected case, you could have element outside of this, they don't have any linear. You see, this is not that. But in the simply connected case, it does. So what is the relevance of this kind of algebraic structure? First, there are several kind of systems people study from 70 years, 60 years. Linear and affine system on Euclidean space. You have the drift is an element exactly here. So before that, think about a new kind of system, general. The drift will be here, and all the control vector will be here also. This is a huge. And hopefully, if someday we have a complete characterization, should be here. Because contain many, actually all, the system we know that contains some algebraic structure. For example, invariant systems of Lie group, bilinear system, linear systems of Lie group, and many, many applications. Let me give you a couple. Everything. The drift is a sum between invariant and a linear, also any exact. This is huge. Actually, all these systems are particular cases of this huge. Yes. So, okay. So let me give you a concrete example. So we define linear flow, as I said before. We impose the hypothesis of the flow of the vector field should be a one-parameter group of automorphism of G. And it's very easy to show that these vector fields define a Jacobi identity, give you a derivation associated. And here are the formula from, this is very nice diagram in Lie groups. So you have a connection between phi t, between the flow and the matrix D. Of course, since the group is connected, we know that any element of the group is a finite product. Since phi of t is automorphism, you can separate and then you can compute. Actually, phi t of x for any x in the group. Okay, I say if you can compute, but you need to know to compute this. If you know the spectrum of D, you use linear algebra, and that's it. But other cases not. So here is very specific, concrete example on the Heisenberg. This is, we take this basis, x, y, and z with the bracket. So very easy, you show the derivation are a 6-dimensional algebra. And here is the linear vector field associated with any derivation. You see, this quadratic element shows that the name of the system is not so happy. Actually, if you consider a thin group of dimension 3, it appears natural logarithm. It is very nonlinear, but okay.
But in some sense, generalized.
Yes, of course. It's yes, the name. We were thinking with Adriano da Silva and João to change to automorphism, but there are a lot of papers, right? It's very complicated to change. Okay. So we have from linear on Rn to linear only group, which means X is a linear, which we ask for the flow is a one-parameter group of automorphism. And here you take just invariant, of course. But why you need to study all this stuff? After 2 days, I was thinking 2 days and drinking something, I came with the answer. This is a kind of why, but better, right? Yeah, this is perfect answer. Remember, I am coming from Chile. No, also it's mathematically interesting. Typically when you work in differential equation on Lie groups, when you drop the parentheses, you are in Rn, some Euclidean space. So you have some normally differential equation on Euclidean space, but you know more because they have a intrinsically structured geometric structure. See? Other good reasons are the Johann equivalence theorem. If you have any manifold and very general vector fields at the beginning, x and yy, yj, if you take the algebra of x and yj, and if they generate a finite dimensionally algebra, so you prove that you have two possibilities. If x has a singularity, then you have a linear control system. If not, you have an invariant vector field, invariant control system. So it's a very nice theory because, for example, take any paper, for example, in IEEE, many papers that the people try to understand, they cannot, they use numerical analysis, for example. But if you are lucky and you have this condition, then you compute the group, go to the linear system, we have a lot of results, and then, you see, it's a machinery of bill papers. Right? Applications. Well, the first one is the more important. And also, you have a concrete application. For example, you want to control this satellite. The differential equation are inside of the Lie algebra of this group. Right? This is an orthogonal group, rotation, and this is define the Euler's angle. This is, for example, very famous. You know the brachistochrona? Of course you know. You have 2 points here, and you need to find the shortest path connecting. So you need to give me a curve that I can reach this point in minimum time. This problem changed the mathematical, right? Mathematics is changed after this. People say that some guys find the solution. Actually, it was a challenge between brothers. Yes, and after 6 months, the brother couldn't be successful, and Leibniz decided to give an extension. And someday, this this journal received a solution of the work, but with that author. Nothing, just the solution. And let me say, okay, so should be Newton. Nobody else, of course. Well, what is nice here, if you put coordinates here, x, you see, you have xy here, xy, and then you have this derivative of this. You have four. I have problem. 4. And you can write all this equation about this problem through this 4 differential equation. G is the gravitational constant. And look, consider the vector x, v, w, 0, minus g. And the vector y, 0, 0, minus w, v. So here you interpret all this differential equation through this system, right? And take the Lie algebra generated by the system. This is called this Lie algebra is called the diamante, l'algebra diamante. It's solvable. What is interesting, all these people, when they solve this problem, you have the conservation law, potential and cinetic. You see the same. But through the control theory, you don't need any, because this give you this Lie algebra give you by the Frobenius theorem. This is of course is integrable on R4. You have a foliation by differentiable manifold of dimension 3. So this function E is the energy. Do you remember when you have a foliation like from a Frobenius theorem, you have an orthogonal, which is the derivative of the function. So here the energy is constant. So you don't need to assume. So give me a point in a leaf, I tell you the solution without any, right? And explicitly given by this expression. Okay. 2006, I was in this meeting. Some guy was the idea to include these people here in our invited session. So they were working and how to manage the medicine, you know, to give the people, because normally this is just from a statistic and this could be very dangerous. But the model was a bilinear system determined by two matrices, A and B, and these matrices are in SL2R, right? So first you need to know if the system is controllable or not. If not, you need to find a control set region. But some years ago, 1999, we published with Luis something about controllability. Also Braga is people from Maringá. But this was a geometric idea. We considered the Cartan killing form, and we considered the associated quadratic, and here is the basis. So give you on R3 a beacon, the zeros of this quadratic form. And like before, the control here is the same. Local integral function. And we prove that the system is controllable if and only if you take the point A minus B, here is A, here is B, A minus B, and the point A plus B, which means to take the control 1 and minus 1. And consider this line. okay, the theorem is the system is controllable if and only if the line intersects the interior of the beacon. Inside you have all rotation. Outside they are diagonal, and in the boundary you have nilpotent matrix, right? So we show this stuff for them. They will happy.
I think I didn't understand. There is a line segment between A minus B
and A plus B. This segment,
and if the segment intersects the interior of
the cone, so it's controllable.
But it isn't it's sufficient to one of the points are inside the interior of the cone?
No, just one point of the line.
Yeah, but this if and only if one of
okay. Because you can have both outside and
yes.
okay.
And something more. If you are here, for example, and you have this situation, right? So you put your hand in your pocket, pay more for the controls, and then it's possible because you extend. There is some control set associated with this. So if you extend, the line could go inside. So another thing is the control set, the associated control set explodes. There is explosion. Because before, up to reach, this is a subset of the group, or R2 here. But when you enter, it's all the, so it's something like a lower semi-continuity with the hydrometric. Here is the starting point. I explained. It was in ICTP. So this is it's very old, 1999. What do we do? First, you remember you have x dot ax plus bu. So, for example, if x equals 0, you just move on the direction of bu, right? It's like when you go to park. This is the place when I want to park, and I am here. Of course, normally the car, you don't have this direction. So you need to go something here, and, it's something like you do something similar, very similar to Lie bracket. And why? They show Rashevsky theorem. When you have a family of vector field, they don't generate all the space in any point. For example, in this case, you see, in this case, VU didn't give you all the direction, but the vector fields associated with this, the Lie bracket between these vector fields generate all the space, then you have a metric. Any 2 points can be connected. But they are admissible curves in the sense that, for example, here are the restrictions, plane, for example. So the curve should be tangent to the plane. You cannot go up. So at any point, you see, this is the sub-Riemannian geometry. So consider first the Lie algebra generated by the vector fields, and then this is the smallest. You see, there is it's the Lie algebra generated by x and y1, ym. The smallest at x subalgebra of G containing H. Do you remember B, AB, A minus 1B? You can define this vector, the vector space generated by the column vector as the smallest A invariant subspace containing the image of B. Exactly the same. So this is the Lie algebra associated with the system, and here is the Lie group with this Lie algebra. Of course, it's the same. It's the smallest invariant by the flow, subgroup of G containing the subgroup H, with H is exactly the Lie group with this Lie algebra. So Lie condition means that this algebra should be G. Why not? Otherwise, what happened? Again, for the Frobenius theorem, you will have a foliation. But if you start here, since they are connected, you can never go outside. So your problem is malposed, is bad posed. So you can ask. Yes, of course. Exactly. Well, with Professor Tirado, we characterize the normalizer. We define this new class of system. We prove that at rank condition means you drop LA. You just take this and take the vector, the adjoint, but you don't consider the Lie algebra. This is more strong. And then you can prove that you have controllability local at the identity. That's it. And we show the shape of the solution of any element in the normalizer. You see here is very similar to the expression of on Rn, but not integral, but a series. See? Anyway, these elements are polynomial, homogeneous, blah, blah, blah. Anyway, this is very important point, very important difference between invariant systems and linear systems. What is invariant system? Invariant system, the drift is invariant and the control vector are also invariant. So why is different? Because since we assume the groups are connected, if you have a neighborhood of the identity, you know, it's very easy to know that the powers, the union of the power catch all the group, right? So essentially, it's very Sussman, you know Sussman. He's from Argentina. Hector Sussman. No? I introduce you Hector Sussman. Okay, now he's working in Roger many years. So it's outside of Argentina many years. Roger. He proved that in the case of invariant, the accessibility set from the identity is a semi-group. So you see, this is a local. Controllability is a local problem because if you have a local problem, the power which is inside of the semi-group will give you all the group. But this is not the case for linear. This is very different. This is the reason why this system is very more complicated than the invariant case. And with San Martin, we proved some results. Okay. Now let's go to some groups. What does it mean, the Kalman condition? The Kalman condition means that the vector space generated by this guy, which is vector space, is open. So coincide with the vector space, Rn. So here, the natural condition, necessary condition, is to assume that the accessibility set from the identity is an open set. Then we have the same result for controllability like in Rn, exactly the same. Okay. Again, controllability is an exceptional property even in the unrestricted case. We published recently, well, 2 years ago, to obtain for this kind of Lie groups something similar, but just this condition implies controllability, not the opposite. It's not equivalent. And we need to assume something about the group we call finite semi-simple center, which means all the semi-simple group, they have a finite center, right? With this condition, we prove the same result that I explained, and a little bit more. For example,
why is necessary?
This is a good question. But normally, this condition is equivalent to your maximal compact group should be compact.
Okay.
And you need to do that, right? This is the name is a little bit, but that's it. That's it.
What's the spectrum Ly?
Sorry, Lyapunov, just the real part. Sorry. Lyapunov effect, just the real part. So we prove several things. The existence control set is closer if the set you can translate to the identity coincide with the group. It's open when the accessible set of the identity is G. In the nilpotent case, we obtain again the same that in the linear case on Rn. And if the Lie group is solvable, this control set is unique. And we have something about some condition to show that in some cases the control set is bounded. And look, C is closed if and only if D, you see, has only eigenvalue with non-positive realm, and it's open in the other direction. So, since C is, in this case, C is open and closed, you have C equal G, right? So what kind of mathematics we use? Well, first we consider, you see, everything depends here on the linear vector field, like in Rn. Many things. So we decompose, we consider the generalized eigenspaces, and we compose this G, the Lie algebra G, in 3 Lie subalgebras. They are nilpotent, and this is the central part. And you can prove, for example, for solvable case, you can prove that the Lie group associated with the Lie algebra, which contains G plus 0, the sum of this Lie algebra, is contained in A. On the other hand, this containing, so you see, it's something similar as before. See, if there is no plus, no minus, you have controllability again. So this is the meaning where it, I mean, this is exactly what happened in general group solvable here in Rn. It's a nice generalization. Now you have restricted case and control set. This paper is very recently. We characterize for dimension 3 solvable non-impotent when the system is controllable or when not. And you see there is a very nice classification of CONICYT. You have all this possibility for the Lie algebras. Then you consider the Lie group. I am not going to show, but the idea is there was a paper from João and that they analyzed controllability for solvable case in dimension 2. So we project. That's it. You see? This is another paper in the semi-simple case. Contrary to the solvable case, there is one control set in the identity, but there are more. These are translations of the control center of the identity by some element of the Weyl chamber. So here is, all this stuff, heavy machinery from semi-simple Lie groups. In two-dimensional case for solvable Lie group, we compute everything. what are the phase of the linear vector fields, what are the phase of the invariant. We compute the general system. Here are the equations. And by considering different parameters, A, B, alpha, and beta, we prove that they are the control set. So you have non-numerable control set, this situation, numerable but with empty interior. Here again, this case is empty interior. Here is the only controllable. Control set. Well, an equation for the complicated calculus in the previous paper. This is the phone number of Adriano, of course. Now, let me say you something about Adriano. This is a very talented mathematician, very young and talented mathematician. But also, this is very good for computation. So please call this number. Okay. Pontryagin Maximum Principle for Linear Control Systems Only Groups. Well, we published this paper 2016 with Philippe João, but in different situations we were working in almost Riemannian geometry. How many? 5 minutes. Okay. So here is the system, and as usual, you take the Hamiltonian. You see, you look what happened with the system in the quadrature bundle, right? So you need to lift all the invariant vector field, and you need to lift the linear vector field, and to compute the differential equation. You see, they are the differential equation. Of course, the first one is the same as always, because the solution, the maximum principle, the idea is, do you remember Lagrange, right? Here is, but you double. You have dimension m, you go to the tangent bundle, the dimension 2m, and you have your equation here. So the first component is your solution here. You see? Because this is the first equation. So you use all this stuff to find some integral curve we call extremal, which are, they optimize some special here, and then you project. So any optimal solution here is coming from the lifting. You see, the second equation just depends on D, of course, and the adjoint of all these vector fields. No, I don't intend to talk about that. I believe I have 3 minutes to solve the problem of the train. So, do you remember this? The point you want to reach should be in the boundary, right? But this is in the proof of the Pontryagin Maximum Principle. It's happening in some infinite dimensional spaces, like functions. But the important thing is the fact that the point should be in the boundary implies, after 30 pages, that your the optimal contours are in the boundary of the omega. This is extraordinary. So, according to Pontryagin Maximum Principle, do you remember? You need to consider just two controls. the equation is x equal y and y equal minus 1, you see, plus minus 1. So this is our parabolas. And for the case u equal 1, you have parabolas also. So here you have two important curves. Oh, no. They are the curves that transport you to the region. So assume you are here. The Pontryagin Maximum Principle say you that the optimum, you need to consider just two controls. Among all the possible, local integrable, you have huge, but you just two. U equal minus 1 or u equal 1. If you start here, and then you have with velocity here, if you break, you go far from the region. So, according to that, I need to consider u equal 1. All right, equal 1. Up to where? Of course, up to this point. So the driver, the computer know very well these curves. Given the initial position, they know all this stuff. So he knows the intersection. In particular, he knows the projection. So starting here, the driver should apply u equal 1 up to here. And then you break with minus 1, and then you stop here. Right? Now assume you are here. You are very near to the station, but with very high velocity. So, according to the maximum principle, I cannot accelerate. I need to consider the brake. Here it happens something strange because I need to brake, but here is 0. I need to brake. How is that?
You need to pass,
Then you use the reverse. You use the reverse up to here, and then you take u equal 1, and you stop. Well, this is the way when, when some satellite go, some landing or everything, in robotic, and this is the way. This is just very simple example, but contain all the many ingredients of the theory. So I will let you stop here, right? Yes, we have. We have a paper. We have a paper. We have some sufficient condition for bounded. Just in sub-Riemannian case. And the example we have is a listing of the example of the Colonius and Kliman. Yeah, all right. But we have others now. Adriano, he has an idea to write a book to say everything about controllability, control set, and maximum principle up to dimension 3. On the other hand, we have with Adriano and Philippe Jean from Rouen University in France, we start a project to write down a book of linear systems. It's time. It is time. But answer your question, yes, but not too much. Okay?
Have you considered discrete time controls?
Yes, but not in this.
Because I think it's a little bit more tricky.
Yes, you are right. I mean, we have a paper with San Martin, and when discrete, we consider discrete.
But
Non in linear, in bilinear, and on Rn.
okay.
When everything is matrix, you see, it is different. So it's a good question, but I'm sorry.
Okay.
And even, we had so many problems, you see, about that. We were starting to contract to understand all this stuff, but it's very complicated. And the next step is to consider system in the normalizer, but this will be for my, I don't know.
For the boundedness of the control set, do you have to assume that the center is finite?
What?
Do you have to assume that the center of the group is
Yes, yes. We need to do that. Otherwise, it's not. Okay. I mean, why we came from this condition? First, we proved for solvable, right? Of course, it satisfies this condition, and then we realized that some paper of San Martin, when he doesn't have the condition of the center, some semi-groups they do not act in yes. So we think, okay, let us try, and it's possible. Yes, exactly. You mean that's right. Alexander.
You said about controllability of linear system in three-dimensional because use that approach to project.
In 3 dimensions, and then we project to that 2 dimension. Yes.
But we tried some time ago to
Directly.
Yes, in the 4 dimension, but the problem.
And the 4.
The problem is that in the 4 dimension, if you use the same approach in 3 dimension case when you project, the 3 dimension case is not a group, so it's not possible to use the previous result.
Well, something you need to do is to start with homogeneous spaces.
Yes.
That's it.
Choice a good homogeneous space.
Yes. In some sense, this is the theorem of Philippe, because it's in the homogeneous space. But you need to add an additional condition for the derivation. It should live invariant the Lie of the subgroup. So you reduce a lot of your possibility. But it's a good point. See, homogeneous spaces. Thank you.